Hello friends, MoNaCo here again with our 8th homework note video for atomic theory. Today we're going to focus on Lewis or electron dot diagrams. The reason why we call them Lewis dot diagrams is because there was a chemist that pioneered this process, and his name of course was Lewis. Now if you remember last video, video 7, we did Bohr diagrams or Bohr models, and that showed the nucleus with its protons and neutrons, and then it showed all of the principal energy levels and where all the electrons filled in. So it was kind of like, this with all the rings on it, and we filled in electrons, et cetera, et cetera, et cetera. As you get to more heavier elements and larger numbers of principal energy levels, all of a sudden your Bohr diagrams get absolutely huge. So Lewis wanted to come up with this idea, a way of showing a model of an atom that represented only the protons, neutrons, and valence electrons. Why valence electrons? Well, the valence electrons have everything to do with what elements will combine to form compounds. So he wanted to condense all the information that was in a Bohr diagram into something that was faster, simpler, and easier to use, but still had basically all the information that he needed. So here it is. Bohr models were just great, but we had to simplify them. And so you see in this image, we have the element symbol at the center of the diagram, and then the unpaired valence electrons go around the outside. Electrons do like to pair up in buddy systems. That's why we allow them to have 2 on per side, but generally speaking, they spread out when there's unpaired electrons so that they all occupy their own side. There is a method to teaching you how to put in your electrons, and I'll show you that in a moment. So in your notes, we're going to cover the electron dot diagram. So they only illustrate the electron configuration for the valence. So they only show you the outside electrons. Then we write the element symbol, and we retrieve the electron configuration from the periodic table. The last number in the configuration is the number of valence electrons. Okay, so we would write the element symbol, and then we just put the valence electrons around the outside. Here's how we do it. We arrange the electron dots, the valence electrons, around the symbol using the following rule. Only 2 electrons maximum per side, and no more than 8 around an atom. Okay. Always pair the first 2. Why? Has to do with valence shell electron pair repulsion theory, VSEPR, which is an AP Chem topic, but we're going to practice it because that's the best way to do it. If you have more than 2 valence electrons, deal them one at a time to the other 3 sides until you run out. So it's like dealing cards. It's like the first person gets 2 cards, and then each other person around the table gets 1 until all 8 cards are handed out. Okay. Sometimes you can go 1, 2, 3, 4, 1, 2, 3, 4, but generally speaking, you always put the first 2 first, like 1, then 2, and then you go 3, 4, 5, 6, 7, 8. So it's like the first player at the table gets 2 cards, and then everybody else gets 1 until everything's full up with 8. You could use dots or X's when you're counting and putting the valence electrons out there. It doesn't really matter. You just want to be consistent. Okay. Now, if you're working with an ion, you've got to adjust the valence electrons. So you got to add or subtract those. Again, remember, if you have a positive ion, you have a lost electron, so you must subtract them from the electron configuration on the periodic table. And if you have a positive ion, you have gained electrons. So example is sulfur, -2. So you have to add 2 electrons to the 6 that S normally has in its valence shell. You'd find that by looking at your periodic table. There are 6 in the valence shell, so you have to add 2 electrons to it. Notice how negative ions always end up with 8 valence electrons. Notice how we have our S, and it's got 1, 2, 3, 4, 5, 6, 7, 8. The fact that there's brackets is important. The brackets are there to show you that it is an ion. In this case, an anion. Anion. Now, on the other side of the coin, we have a positive ion. So K plus 1. Remember, you have to remove an electron from the valence shell of K as it's written on the periodic table. And in this case, we will not have any valence electrons around the potassium because there's been all removed. So you draw the brackets to show that it is an ion. What type of ion? A cation, because it has a positive charge. And now positive ions always end up with 0 valence electrons. This is the rule of how atoms become ions by giving or gaining electrons. And they follow these two rules. You always either end up with 8 valence or 0 valence. That's kind of how it works. So let's draw some Lewis electron dot diagrams for the following. I'll cover a couple atoms and a couple ions apiece. Okay. So argon. I find the element argon, Ar. I start by drawing the symbol in the middle. Then I look at the element agar on my periodic table, and I see that it has 8 valence electrons. So what I will do is I will draw in the first 2, like a pair, and then I'll deal the other 3 out, one at a time, until I have filled up with 8. Done. Okay. Let's do aluminum next. Aluminum. Well, you start with Al for the element symbol. You look at your periodic table and you see, well, it's the electron configuration is 2, 8, 3, so there's 3 valence electrons. The way to do it is you give the first 2 a pair, and then you put 1 by itself. That's it. That's how easy the simple neutral atoms are. Let's look at these ions we've got here. N3 negative. So nitrogen 3 negative. Well, we start with the same way. We put the N in the middle. Now, the only extra step is that we have to remember there's 3 negative extras in this ion. So there's 3 more electrons than my periodic table is telling me. My periodic table is telling me there's supposed to be 5, but I have to add 3 to that. So there's going to be 8 around this particular ion. I'm going to put my 2 dots in. 2, 3, 4, 5, 6, 7, 8. Don't forget, since it's an ion, you've got to put some brackets around it. And then the last little bit is you will take the charge and put it in the top right corner. 3 negative or negative 3. Either way, you represent that. It is equivalent. 3 negative and negative 3 are the same thing when we're talking about ions. So that's a negative ion. Let's do this positive ion for sodium. Same way we start, Na for our element symbol. And we look here, we say, okay, it's a +1 ion. If I look at my periodic table, oh, geez, I've only got 1 valence electron. And since I've got a +1 ion, that means I've got more positives than negatives. It means I've lost an electron. So there's no valence electrons for the sodium ion. There are no dots to draw in, but there are brackets and +1, the ion oxidation state, to draw in as well. Oxygen is very simple, similar. Above we have the oxygen atom, which you can see on your periodic table has 1, 2, 3, 4, 5, 6 valence electrons. And down below we have the oxygen ion, which has 6 valence electrons plus 2 more because it's a 2 negative charge. So we got 8 total valence electrons around the oxygen ion. There we go. So we got to put our brackets around it because it's an ion. And then we put our charge in the top right corner because that's where it belongs. Okay? So a quick note. The number of unpaired valence electrons is equal to the number of bonds that an element can form with other elements. When determining the number of bonds an element can form, you got to arrange the valence electrons so that you have the maximum number unpaired. Okay? For example, carbon can be arranged in either of 2 ways shown on the previous page. Draw the Lewis dot structure for carbon that gives it the maximum number of unpaired valence electrons. So we're going to do carbon. Looking at our periodic table, carbon has 4 valence electrons. So we're going to maximize the unpaired. So in this case, we're not going to put the 2 together. We're going to just go ahead and throw them around at the 4 corners. How many bonds can an atom of carbon form? Well, it has 4 valence electrons. And the number of bonds it can form with another element is the number of unpaired valence electrons. So it has 4 unpaired valence electrons, so it can form 4 chemical bonds with other atoms. The alternate Lewis structure for carbon with only 2 unpaired valence electrons represents the lowest energy state of carbon. Okay. So here we go. We got some practice. These are Regents type questions. What's the advantage to using the Bohr model as opposed to the Lewis model? Answer it. What's the advantage to using the Lewis model as opposed to the Bohr model? So each model has slight advantages over others. Can you figure it out? What's the maximum number of electrons an atom or an ion can have in its valence shell? What's the maximum number of electrons an atom can have on its outside shell? And what's the number of bonds an atom of an element can form is the same as the number of We just covered that with carbon. An atom of which of the following elements can form the most bonds? Hint, you got to look at your Lewis diagrams, okay? So look back at your Lewis diagrams, see how many unpaired electrons you got, and you can figure out which one's going to form the most bonds. It's all about, bonding's all about unpaired electrons. Well, anyways, here, now you should be able to use that periodic table to make simplified drawings of an atom or an ion in the Lewis dot diagram format. This only shows the element symbol, the valence electrons, and any charge that the ion might have. Thing to remember is if you have an ion that you're trying to represent, you have to add or remove those electrons from the electron configurations so that your Lewis dot diagrams are correct. Thanks for watching, everybody.